In this video, we'll be wrapping up all the concepts of finding the zeros of a polynomial. Now, before we do that, let's talk about a property of a polynomial and their zeros that is extremely important to evaluating and identifying all the zeros of any polynomial. Now, keep in mind, this is all. This doesn't say find the possible rational zeros. Notice this doesn't say find the number of positive or negative real zeros. It simply says find all zeros. So that means that this could imply that there are imaginary zeros. Now, one note about imaginary zeros. If x equals a plus bi is a zero, then x equaling to a minus bi must also be a zero. What this means is that if a polynomial happens to have an imaginary zero, again that I term means that it's imaginary, then the polynomial must also have its conjugate imaginary zero. Again, notice that this multiplied by this, the a plus bi times the a minus bi, will cancel the i's out entirely. So the concept here is that if I have to find a zero that's imaginary, then I might as well use the quadratic formula, because the quadratic formula will identify what those two imaginary zeros happen to be. So, looking at this example here, I'm going to keep that in mind just in case if it pops up. Now, but keep in mind also that I'm not going to do any of this imaginary work here until I get down to some form of a quadratic, because it can't be solved otherwise. Well, if my goal is to find all the zeros, I'm going to go ahead and first start by trying to find a set of values that I might want to work with. PRZs is the first thing I'm going to go ahead and do. Remember that the PRZs, I'm always going to go ahead and take the last term and the first term, and I'm going to find the factors of each of those. So 1 and 24, 2 and 12, making sure I very carefully putting commas in here, 3 and 8, after 3, I'm going to have 4 and 6. And it looks like 5 is not the next one, and that's going to be the end of where my values are. For 4, I'm going to have simply 1, 2, and 4 again. Now, you'll note, again, it's the factors of the last divided by the factors of the first. But when I start writing these PRZs out, you'll notice that I'm going to get a large number of possible options to work with. Let's see here, plus or minus 2. Plus or minus 2 over 2 is 1, don't need it. Plus or minus 2 over 4 is 1/2, I don't need it. So I'm going to go plus or minus 3, then plus or minus 3/2, then plus or minus 3/4. Now, again, note, it didn't ask me to find these PRZs. I'm doing this because this is a step to finding all the z's, all the zeros. So my next step is after 3, I'm going to check 4, so plus or minus 4. Again, remembering that I don't need 4 over 2 because it's just 2, and 4 over 4 I don't need because it's just 1. So I'm going to go to 6 next, which is simply plus or minus 6, then plus or minus 8, then plus or minus 12, then plus or minus 24. Now, I believe 6, if I go through these, 6 over 4 is 3, 6 over 2 is 3, 6 over 4 is 3/2, already have it. 8 over 2 is 4, already have it. 8 over 4 is 2, already have it. 12 over 1 is 12, I don't have that. 12 over 2 is 6, I already have that. 12 over 4 is going to be 3, and I already have that. And then 24 over 1, 24 over 2, 24 over 4 are values I already have. So this is my list of PRZs. Again, the argument is this is the set of numbers that I should attempt to divide this polynomial by in order to find a possible, or in order to find a starting zero to continue the division. Well, this seems like a lot of numbers to try. So what I'm going to end up doing is I'm going to go ahead and find the number of positive real zeros, and I'm going to find the number of negative real zeros as well. Okay, by finding these two values, it might give me a good starting position of where I want to be. Well, if I do this, I'm going to go ahead and count the sign changes. There's 0, 1, 1, 2, and 2. Now, you'll notice that the way I counted that carefully, it goes from positive to positive, which is 0, positive to negative, which is 1, negative to negative, so it's still one sign change going from here to here, and then going from here to here is 2. Notice positive to positive doesn't add a sign change. So the number of positive real zeros is 2 or 0, which is unfortunate because that means that there could be some or there could be none, and we don't know whether or not we should be testing the positive ones or the negative ones yet. Now, for the negative ones, remember, we have to find out what f of negative x is. Now, I'm going to be very, very lazy when it comes to evaluating this. I know that all of the even terms will remain the same sign, but all the odd terms will change. So I know there's going to be negative 4x to the 5th, plus 12x to the 4th, plus 41x cubed, minus 99x squared, minus 10x, plus 24. Again, one more time, all of the even powers will have the same sign they started with, Okay, but all the odd powers will change in sign from what they started with. So now you'll notice I have 1 sign change, 2 sign changes, and 3 sign changes. Again, just to be sure, 1 doesn't change here, 2 doesn't change here, 3. So in the negative case, I'm going to have 3 or 1, which is extremely vital to the conclusion, which I guarantee there has to be a negative real zero. So that tells me that in this entire set, I should start with the negative numbers first. Don't start with the positive ones because I don't know that there's necessarily going to be a zero that's going to work for that. So in this case, our next step is to take this polynomial, which I'm going to rewrite down here. You might see it off, you might not see it on screen, but very carefully rewriting all of these terms, all of these numbers, leaving out all of the powers because I don't like long division. I would so much rather use synthetic division. I didn't leave myself quite enough space here, but that's okay. It'll be fine in terms of how much work I need to actually write. And double checking this again, notice this is negative x, not the original function, so we're not comparing this to these numbers. But let me check back up here. It's 4, 12, negative 41, negative 99, positive 10, positive 24. Secondly, 5th power, 4th, 3rd, 2, 1, 0. Remember, if there happens to be a missing power in the original function, we have to make sure we include a 0 in that spot. So I'm going to go ahead and start with the negative PRZs, and in that case I should start probably with, say, negative 1. Now, in negative 1, I'm going to go ahead and carry down the 4, multiply negative 1 times 4 and get negative 4. That gives me a value of 8. Negative 8, negative 49, positive 49, negative 50, positive 50. And right here, this is the argument that I know I can stop. And the reason why I know I can stop is because in my head, I'm working 2 steps ahead. I'm doing in my head 10 plus 50 is 60. 60 times a negative 1 is something that is much larger than 24. And remember, for us to actually find a factor, the remainder needs to be 0. And I know that negative 60 plus 24 is not going to be equal to 0. So I know right here that 60, negative 60, negative 44 does not equal to 0, and therefore x equals negative 1 is not a factor, or at least not a 0 of this polynomial. Now keep in mind, again, looking at this list, I've gone through negative 1 first. I should probably just move down the line and check them all. There are easier ways to simplify this and make it a less tedious and obnoxious process, but again, for right now, this is the skill that you're going to have down. So I might as well just jump straight to the next number, negative 1/2, which gives me 4, 12, negative 41, negative 99, 10, 24. And I'm going to very carefully here box some of these things off. And now if it helps, by all means, put an X through it because you know it didn't work. But it's good to not scribble it out, erase it or anything, because we still need to be able to see the work that you divided this, did it correctly, and maybe there was a mistake in here that needs to be seen. So for this negative 1/2, I'm going to go ahead and draw this line, carry this number down. So 4, negative 1/2 times 4 is going to be a negative 2. So very carefully, that's going to be 10. 10 times the negative 1/2 looks like a negative 5. So this might get a little bit hairy in terms of the numbers, but oh wait, nope, that's going to be negative 46. Negative 46 times negative 1/2 is going to be a positive 23. Adding these values together ends up with a, looks like 76, and that's a negative number, just to double check, yep. And then negative 76 times a negative 1/2 gives me a positive 38, I believe. And then positive 38 plus 10 is a 48, and then 48 times a negative 1/2 is a negative 24. And look at that, we have a 0. So I needed to get to this point at the very least. We've got to find the remainder of the zeros, but how many zeros do we have left to find? And how many did we find? Well, we found x equals negative 1/2 is a 0. Okay, so that's going to be part of my final answer in terms of lists. Next thing I also want to note is that this was an x to the 5th problem to start, yes? So this down here is a 4x to the 4th, and so on and so forth. Now, once you've found your first 0, now keep in mind I found one of them, so now it's grab bag for whether it be positive or negative that's going to work. But we should always first off attempt to check the negative 1/2 a second time, because we don't know whether or not it's going to work. What I mean by that is this. In my problems, anytime I found a 0 that's going to work, I should, with my quotient, because remember, the intent is that this thing has been factored out. So this thing up here has now been reduced by a single power of x, and I have a new polynomial, this thing right here, that's being multiplied by it. So if I were to go through and again check this, this actually will not be equal to 0, which again means that this thing is not a 0 twice. So again, if this did work, we'd get x equals -1/2 times 2, or with a multiplicity of 2 is what I should say. And that means that we end up finding 2 of the zeros out of the total number of zeros we should find, or 5. Now, to finish this problem, you're simply going to work with this reduced polynomial, which remember, this reduced polynomial is 4x to the 4th plus 10x cubed minus 46x squared minus 76x plus 48. We're going to use this polynomial with the same exact PRZs to attempt to find the rest of these zeros. Now, for you to do this completely and clearly, you will end up finding that the values are x equals 3, x equals -2, x equals -4, and x equals 1/2. Okay, those are the 4 other zeros you're going to find from this after work and deliberation. Let me show you one more example of how this works. I'm going to have 4, 10, -46, -76, and 48. You must show all of this work. So I'm going to check 3 first, just because it happens to be in my list first. Carry down the 4, multiply, gives me 12. Add 22, multiply, gives me 66. Add gives me positive 20. Multiply gives me 60. Add gives me -16, and multiply gives me a -48. So sure enough, there's my remainder of 0. And now I have a factor that is x plus 1/2. I have a factor that is x minus 3. Again, this is for my first synthetic division that worked. This is for my second synthetic division that worked. And my leftover polynomial that I'm now going to be working with to find the rest of them is 4x. It was to the 4th. Now it's cubed, plus 22x squared, plus 20x minus 16. Again, now we're going to work with this polynomial and try and reduce that one, dividing it by this one, and this one. Again, these didn't come out of nowhere. These came from testing these possible values. Okay, so you're going to have to go ahead and work through ones that don't work and work through ones that do, and every time that you find one that does, use that new polynomial. So next I would use -2 with this 4, 22, 20, -16 to show that that one worked as well, and so on and so forth. Again, these problems are long, time-consuming, and tedious, but the intent is that you're going to do all of the work to find the zeros of these polynomials without any calculator, unless you're doing simple arithmetic.